Hello, everyone. Thank you for giving me this opportunity to talk to you about the LoRaWAN protocol. I will show you how it is low power and scalable, particularly when it comes to security. But first of all, I will start with the difference between LoRa and LoRaWAN, because this is a question we often have. So it's very simple. Both are great and work together. LoRa is the radio modulation, the radio link between an end device and a gateway. This radio link is very long range, from 5 kilometers in urban environment up to 15 kilometers in rural environment, and our record is 800 kilometers from a balloon to the top of a mountain. This protocol, this radio link, is very low power, thanks to its low transmit power and its low reception complexity. Specifically, there is no need for prior synchronization in frequency or time. As soon as you open the receiver and there is some signal to receive, this signal is acquired instantly. So both properties are used by LoRaWAN, which is a protocol to build interoperable networks over LoRa. So it's LoRaWAN is a wireless network standard for scalable interoperable deployments. It brings on top of the LoRa range to build wide area networks. And the protocol itself is very low power, and you will see that later in the presentation. The protocol overhead is only 13 bytes. There is a persistent connection to the network, meaning there is no need for constant signaling to stay connected to a gateway, because basically an end device stays connected to a network as a whole. And the devices transmit and receive instantly as they wish, without the need to synchronize to the network before they transmit. They are always, in a way, connected and synchronized to the network. For that, LoRaWAN uses unlicensed spectrum in the sub-gigahertz band. It's possible to do roaming between networks, and very importantly, the LoRa Alliance, so which is responsible for the LoRaWAN protocol, performs the end devices certification. So we have more than 450 end devices types certified. So if you take any of these end devices, you're sure that they're going to interoperate with over any LoRaWAN network. There are today, and this is growing, 156 LoRaWAN network operators which publicly offer services on their networks. These operators are present in 171 countries. And among these countries, there are 27 countries where you can do roaming. So as an example above, so the end device can go to one network or another network. And again, this number of countries where you have roaming is also growing. So to my point of today of security. So first of all, LoRaWAN provides end-to-end security. And I will show what happens to the end device and the network when the device is connected to the network. So the end device is typically connected, from its point of view, to a network server. With that network server, it shares a secret, a key, a session key, which we call the network session key. And this network session key is used to authenticate every message in the uplink or in the downlink, to verify the integrity of the message, that is to verify that the message has not been altered, to prevent replay of the message. And it's also used to encrypt the MAC commands. The MAC commands are the commands which are there to control the network and the operation of the end devices, because the network server is responsible for managing gateways and end devices. It selects which channel, turns on and off the channels, changes possibly the frequency of the channels. It modifies it controls the data rate and transmit power that one end device is using. It sets the downlink reception windows. It sets the timing, the frequency, etc., of really the complete network management. So all this is secured thanks to this session key, which is depicted here in yellow. So now, when it comes to the useful information, the data, so the data is encrypted end-to-end between the end device and an application server. And for this purpose, they share a session key, which is here in green, which is used to encrypt all the application data. So this session key is known to the application server, but not to the network server, which means that the entity responsible for managing the network cannot decrypt the data. The data is only owned by the application. So with these two keys, we have a complete end-to-end encryption and security of the data between the end device and the application, with the network server in the middle, which is responsible for the network. So at the frame level, so in the middle here is the LoRaWAN frame. So what happens at the frame level? So the application data, the application payload here in clear, is encrypted using the application session key, so that green key, the device address, the frame counter, and it goes into this encryption machine, which is a standard AES-128 CTR, which stands for counter, so that AES-128 counter mode of operation, and that gives us an encrypted payload. On top of the encrypted payload, the frame is completed with some link control, the device address, the frame counter. The frame counter serves to prevent replays, and then from all these fields, a message integrity check, a MIC, is computed, again using a well-known security primitive, which is AES-128 CMAC. And to compute that, the network session key, that yellow key, is used to compute the MIC. Only someone that holds this key can compute or verify this message integrity check, which is why the message cannot be altered. Only the end device or the network server can form valid LoRaWAN frames. So the session keys themselves are 128 bits because this is standard AES-128. So the LoRaWAN protocol uses well-known, well-vested cryptographic functions, cryptographic primitives as AES-128. So one mode of operation for encryption, another mode for operation for the frame authentication, integrity protection, and anti-replay protection. And these session keys, they are specific to a device. They are shared secret between the device and the network, and they are renewed at each session, which starts with device activation. So once the device is connected, the session keys are there to protect its security. Then the question is, how are session keys established? Or are they shared between the end device and the network? So here in LoRaWAN, there are two options. The first one, which has a lower level of security, is activation by personalization, or IBP, in LoRaWAN language. And in that case, session keys are set once for all. And the second option is to perform over-the-air activation, where the end device is first authenticated by a third entity, a joint server, before it is allowed to join the network. And it's actually mutual authentication, which is performed by means of an exchange of a join request frame and a join accept frame, and then a key derivation performed from that exchange. And in the second case of over-the-air activation, session keys can be renewed. The session can be renewed, so it's more secure. So the first option is perfectly secure and valid, but it needs to be applied to devices where this level of security is enough. So if you don't need to change session keys. So for that first option, activation by personalization. So there is, like before, two session keys, a network server, an application server. And all this is set up at the beginning before the device starts its operation. So they are provisioned in the end device, in the network server, and in the application. So these session keys, along with the device identity, so which is a unique ID, and I will show you that later, and also the device address on the network. So the end device can connect immediately to the LoRaWAN network server and application server. However, they cannot renew their session, so it's only applicable when this security level is acceptable. Again. So now the second case, it's over-the-air activation. So here we have the the help of a join server and a third key, which is a root key here in orange. So it's a root which looks like a carrot maybe. So that root key is a shared secret between the end device and the join server. And a frame exchange is there to ensure mutual authentication between the end device and the join server. And basically, it's going to be a proof, that exchange, that the end device knows that root key and the join server also knows the same root key. Once mutual authentication is certain, thanks to this exchange, session keys are derived. So the end device derives the two session keys on its end, independently, well, or in parallel, of the join server, which perform the same derivation, and then transfers the session keys to the network server and the application server. If we look at the messages themselves, so here is the join request frame, where this fields, so the device identity, join UI, which is a 128 bits unique identifier, sorry, 64, unique identifier allocated by the IEEE, which identifies the join server, device unique identifier, again 64 bits allocated by the IEEE, which identify the device, a device nonce, which is also like essentially a counter, which is a different number each time we send the join request to prevent replays, and the LoRaWAN header here. And from this, again, a message integrity check is computed using the AES-128 CMAC primitive and this root key. Sorry, the application, the app key, which is the root key of the device. So only the device can compute that, and only an entity with custody of the root key can verify that this message is legitimate. The response is a little bit more complex because it is encrypted. So there is again a message integrity check, which is computed on more fields because there is this header, LoRaWAN header is a bit identical. You just said that this is a join accept frame. Join nonce is again a different number each time, which then comes from the join server. It's to prevent replays, of course. The network ID is the identity of the network where the end device is going to operate. And the device address, well, is the address of the device over that network. On top of that, the network can send radio settings, which are going to help the device using the right channels just after it connects. And all this is encrypted with the same root key. So only the join server can make sure, can sign with this message integrity check the join accept frame and encrypt it. So when the end device receives this, if it can decrypt and verify this signature, it knows that the legitimate join server is talking to it. So then from this join nonce and the device nonce, which was in the join request frame, the derivation of keys happens at the end device and at the join server. So there is no exchange of keys, of session keys between the end device and the join server. The derivations happen in parallel. And what is really nice about keys derivation, that's again a properties of this AES-128 primitive, is that you cannot go back. It's a one-way. You can derive from the root key to the session keys, but if you find one session key, if you guess one session key, or if you manage to open the device and find a session key, you cannot go back to the root key. That's why it's secure. It's okay to have the root key used several times, possibly to do several sessions. And then the last question is how the root keys are shared, how the root keys are established, because that root key is really the foundation of LoRaWAN security. So this is very implementation dependent. The LoRaWAN protocol doesn't tell you how to do that, but what we can tell you is that the correct deployment of root keys is really critical. That's really, since it's the foundation of security, it needs to be well, the keys need to be well transmitted, well injected in the end device and in the joint server, and also well stored. And by well, I mean in a secure manner. So the end state, the final state that we want to reach is that each end device is equipped with its ID, a dev UI, unique identifier, the ID of the joint server that knows that device, so join UI, and its secret, root key, app key, which is shared by the joint server. And basically, the joint server is a massive keyring which holds all the list of the device it knows. And for each device it knows, it knows also the root key of that device, and also, of course, the home network. So which network that device is going to connect to. Because once you need to know that to forward from the joint server to the network server and application server to the right network server and the application server, the right the session keys to the right network entities. So again, it's implementation dependent, and Semtech has done some great job to make that simpler and more scalable. So here, the trick is the LoRa Edge chip, so that's one of our family, it's called LR1110, is provisioned with LoRaWAN root key at production. This means that there is no need to transfer the keys. The keys are there from the beginning, and there is no need to inject the keys, and there is no need to worry about secure storage of the keys, because this is all done by the chip and by Semtech joint server. And the trick for that is to use a hardware security module. A hardware security module is a secured way to generate keys. So at production, on the production line of our LoRa Edge chips, there is an HSM and another HSM which is configured in the same way lies in our joint server. So this is how the root key are injected in the end devices in the chip at production. Then you can build from chip whatever end device you want. And the corresponding, the same secrets are shared with the Semtech joint server. And since it's all based on the hardware security module, it's really, well, it's completely secure. It's not breakable. More on our LR1110 chip. So that's this chip has a cryptographic engine which performs all the AES-128 computation. So it's like a secure element. It stores the root key and session keys, and the keys cannot be read. So you can ask for an encryption operation, ask for a decryption operation to that cryptographic engine, but nothing is going to get out of the engine. You're only going to be able to read the result. You will not be able to read the keys. You will not be able to read the intermediate computation results, etc. And you can rewrite the root key if you don't need to use the Semtech joint server, but that's the only thing you can do. You can write it, but then you cannot read it back. And you don't even read, well, you can't even read the session keys. So the LR1110 comes as a modem version, which means it is equipped with the LoRaWAN stack firmware, which is LoRaWAN certified. So you know that if you build a product from that chip, it's going to be interoperable with all LoRaWAN networks. And again, in that situation, the device ID, the dev UI, and its root key are provisioned in the chip or the module, and in the Semtech joint server, in a way, in parallel. Last but not least, that chip is capable of many geolocalization features, because it has a Wi-Fi and GNSS scanner. So it's really a great chip for asset management. So with this, I am done with this talk. Thank you for listening, and I will be ready to answer questions in a few minutes. Thank you.